This film deals with the Nuffield proposals for teaching atomic structure to advanced level chemistry students. The first section is concerned with revision of the nature of the electron, positive ions, and radioactivity. Since the depth of treatment is bound to vary from school to school, the best advice would seem to be, assume your students know nothing, but that they learn very quickly. A possible approach is a lecture demonstration, in which they are told that electrons were discovered in discharge tubes. Scientists are curious creatures, and having tested solids and liquids for conductivity, they turn their attention to gases. At very low pressures, the cathode rays produced in these discharge tubes cause certain substances to fluoresce, and they are clearly affected by magnetic fields. This is the famous Maltese cross experiment, which shows that electrons travel in straight lines, and on the close approach of a magnet, behave as though they are negatively charged. This is a modern version of J.J. Thomson's classical experiment to determine E over M. A beam of electrons is first of all subjected to an electric field, and then to an opposing magnetic field produced by these coils. The magnetic field may be varied. Measurements of the strengths of these fields and other experiments led to a determination of the mass of the electron. Since the properties of electrons do not vary with the nature of the gas or the electrode in the discharge tube, it seems a reasonable conclusion that the electron is a fundamental constituent of matter. Positive ions are formed by collisions between electrons and neutral atoms in discharge tubes. The simple tube used in the first experiment has a slit in the cathode through which positive ions pass in a direction opposite to the electrons. They are seen as a pink glow behind the cathode. Several simple experiments are available to illustrate the properties of radioactive substances. A Geiger-Muller counter is used to detect radiation and hence to show that alpha particles are stopped by a piece of paper or by a few centimeters of air. Experiments using alpha particles must therefore be conducted in a vacuum. Beta particles, on the other hand, are stopped by metal sheets. This brass plate has a slit in it, which is used to collimate a beam of beta particles. On the approach of a magnet, the count rate drops because the beam is deflected away from the slit. Fleming's left-hand rule may be used to show that the particles are negatively charged. Some knowledge of radioactivity, in particular the properties of alpha particles, is necessary to understand the work of Geiger and Marsden in support of Rutherford's theory of a nuclear atom. Here is part of a film called the Rutherford model of the atom.
Here is the apparatus I'm going to use to repeat one of the experiments that helped to test Rutherford's idea of the nucleus. Here is a gun out of which come alpha particles from a deposit of polonium inside. The alpha particles come out through the hole at the end, the muzzle of the gun. The gun points at a sheet of gold foil just in front of the gun. As I turn the arm on which the foil is fixed, I can place the foil in the path of the particles. There it is, right in the beam of alpha particles. The alpha particles may go straight through, many do, and reach this detector here. But I'm going to swing the detector round to one side to see if we can detect any alpha particles that ricochet off a gold atom at a large angle. Here we are, at a fairly big angle. This lead from the detector goes to these amplifiers, and from there to the scaler here, which counts the particles as they arrive at the detector. I'll switch on the scaler. Now, are any reaching the detector at that large angle? There seem to be a few, but only a few.
The reflections of fast-moving alpha particles from thin metal foils were completely unexpected and led to Rutherford's comment that it was quite the most incredible event that had ever happened to him in his life. Extracts from original papers are frequently quoted in the student's book. They create atmosphere and are a great help in trying to explain what men like Rutherford and Moseley were trying to do. This is a diagram of a modern mass spectrometer, which is used to determine atomic masses accurately. The relative abundance and the masses of each isotope of a particular element are found, and hence used to calculate the atomic mass. The principles of a mass spectrometer may be explained by using this homemade model. This is a magnet, and these ball bearings of different sizes are deflected by the magnet into these pockets. Students must be shown how to interpret results from a modern mass spectrometer. They are also asked to calculate the density of the fluorine nucleus. An answer of over 60 million tons per cubic centimetre is surely good evidence that the forces holding the nucleus together are rather powerful. Thus, at this stage, we have a model of the atom which consists of a small, very dense nucleus surrounded by electrons in an unspecified manner. The rest of the film is concerned with the arrangements of these electrons. In other words, the theory of energy levels. Since this is only a theory, it is important to show that evidence from different experiments supports the theory consistently. Two sources of evidence are quoted: ionization energies and atomic spectra. The practical determinations of ionization energies are difficult, and perhaps the best way to introduce this subject is to use the chem study film, Ionization Energies. In this film, two methods, electron impact and photoionization, are clearly discussed and illustrated by live shots of experiments. The student's book includes this diagram of a typical electron bombardment experiment using a radio valve. The energy of electrons released by the hot cathode is increased until they produce ionization of the gas in the valve. The rest of the apparatus is concerned with detecting ionization and measuring the energy of the electrons. The teacher's guide also includes details of this homemade apparatus for finding the first ionization energy of argon using this cheap valve. The electrons emitted by the cathode are gradually accelerated by a measured potential difference. Until they possess enough energy to remove electrons from neutral argon atoms. This stage is revealed by a sudden flow of current in an external circuit. If the measured potential difference is 18 volts, then the first ionization energy of argon is 18 electron volts. The results of these ionization energy determinations may now be discussed. It is interesting to ask your class what type of graph they would expect for a plot of first ionization energy against atomic number. With no previous experience of the subject, they will probably suggest a continuous curve. But the actual results are dramatically different and may be explained in terms of energy levels and sublevels. A model is now made to help with the explanation, and at this stage, the S, P, and D notation for electrons is introduced. We have produced a theory, and now it must be further tested with successive ionization energies. The student's data book provides the information for several elements. Let us consider the element sodium, for example. The model we use to explain first ionization energies suggests that this 3s electron should be easier to remove than any of these 2p electrons. The datasheet tells us that the second ionization energy of sodium is about 9 times the first, while the next 5 values are of the same order. In fact, if we consider the 11 ionization energies of sodium, the model successfully explains the pattern of behavior actually observed. We now turn to atomic spectra. The class observed the emission spectra of elements such as helium or neon using a direct vision spectroscope or a diffraction grating. This is neon. And this is helium. These observations are supplemented by the reproduction of the hydrogen spectrum in the student's book. The spacing of these lines suggests that some fundamental law is being obeyed. Interpretation is again supplied in terms of energy levels. Spectral lines are rising from electron transitions from one level to another. You will notice that the lines come closer together. At the convergence limit in the ultraviolet series, the electron possesses enough energy to escape from the atom completely. The frequency of this convergence limit is converted into the ionization energy of hydrogen, and this brings together the work on spectra with previous work on ionization energy. Some mention must now be made of the spatial distributions of electrons. This is a diagram showing the density of the electron cloud charge over a cross-section of a hydrogen atom. It is hoped to convey the idea of a diffuse cloud of negative charge, rather than an electron pursuing a particular path about the nucleus. The student's book suggests that the charge clouds of all s electrons are spherical, but the shapes of p and d orbitals are not discussed on the grounds that it is not possible to produce evidence for them. Finally, I would like to emphasize that the ideas discussed in this film are taken from one topic only, whereas the subject of atomic structure is referred to repeatedly throughout the whole course. In common with all NAFIL material, it is presented in the form of suggestions, available for discussion, criticism, and we hope improvement.